वार दिया बेचारे वार चिटी अम्मा मेरी चिटी इतनी प्यारी है बेबी इधर आ नानू चीटू दरवाजा बंद कर दे
जानने के
सॉरी सॉरी बुद्धि अच्छा अच्छा पागल हो गए बाहर कोई भी नहीं दिखा अब इसको देखो उछल करते हैं उछल निकाल इधर आ बाहर को
You're watching a total solar eclipse on Time and Date. We're currently streaming from the Northwest Cape in Western Australia, and we're a little under an hour and 20 minutes to totality. We've got our timeline there showing us that the moon is moving down through its partial stage, inching towards totality there. So if you're wondering about the UTC time, there's also time right below here that you can compare to, so you know what time it is. And we're looking at a telescope image here that's quite overexposed. That's to show those prominences that are coming out on the left. And what exactly are prominences?
Yeah, we're seeing some beautiful prominences, as you say there, Anna, on the left-hand side of the sun in the main image. When we look at those smaller suns on the right-hand side of the screen, it's easy to imagine that the sun is just calmly sitting in the sky, but the sun is just an incredibly active place. The sun is a big ball of plasma, a plasma being one of the fundamental states of matter. We know about solids and liquids and gases. If you heat up a solid, you get a liquid. If you heat up a liquid, you get a gas. If you heat up a gas, you get a plasma, a charged gas where electrons are ripped away from atoms and you have these charged particles moving around. This creates all kinds of magnetic fields, and this is what creates all this activity that we see on the sun, like the sunspots we can see in the small pictures on the right-hand side, and like these enormous structures that we're seeing in the main image, these prominences. These are huge jets of plasma that are being thrown up from the surface of the sun by the intense magnetic fields that the sun is creating. And yes, we can see some beautiful examples of these on the left-hand side of the main image.
So we're looking at prominences, but we're also looking at a solar eclipse. And I can explain a little bit what a total solar eclipse is. So you've got the sun, the moon, and the earth lining up. So the moon comes in between earth and the sun and blocks out the sun's rays. So when you're standing on earth and looking up, you can see exactly what we're seeing here, the moon eating its way into the sun's disk. And during partial eclipse, you can see it. We're not seeing it move really fast. It's kind of slow, but as we get to totality, it moves really, really quickly. only a few things in astronomy happen that quickly. So we're going to be busy at that point, enjoying all the different stages of totality. So don't blink, you'll miss it, and stay here so you can see it.
That's right. Keep with us as we inch our way towards totality, when the sun will be completely covered by the moon, coming up a little under 1 hour and 15 minutes from now. In the meantime, don't forget to check out timeanddate.live for more information about this eclipse, about the people that we're working with, and there's pictures from around the world. And Anna and I will be back shortly.
You're watching a total solar eclipse on time and date, and it's from the Northwest Cape in Western Australia, and we're about 1 hour away from totality, just over 1 hour. We're looking at some gorgeous images here of the moon eating its way over the sun, and just want to remind everyone that telescopes, they flip the images. So we've got the moon eating away from one side here on our main image from MIT NASA Eclipse expedition, but from the other two images, the sun's coming from, no, the moon is coming from the 12 o'clock position. So we're all looking at the same sun, same moon, but it's just the telescope flipping the images around. And like I said, we've got these awesome images coming in from the MIT and NASA expedition. And we had a chat earlier with Dr. Michael Pearson, because he's on site in Exmouth, and he's studying the solar corona. And he explained a few things about the corona, didn't he, Graham?
Yeah, so Dr. Michael Pearson is one of the scientists who is looking into something known as the coronal heating problem. Later on in this eclipse, when we get to totality, we will see the solar corona appear. This is the outer atmosphere of the sun, which is always there surrounding the sun. It's just that we can never see it until the sun is eclipsed by the moon, and then it comes into view. And there has always been a great mystery surrounding the solar corona, because the sun, all of the energy production takes place in nuclear fusion reactions in the center of the sun. And then as you move outwards towards the sun's outer disk, towards the surface of the sun, the temperature goes down, as you would expect. But then as we continue to move away from the center of the sun, away from the sun's surface into the solar corona, the temperature goes back up again. which is counterintuitive and doesn't really seem to make any sense. Now, we think that this is all to do with the sun's magnetic field, but we don't really understand the detail of how this heating happens. So Dr. Parsons' team is looking into finding the mechanism by which the solar corona is heated and which makes it a lot hotter than the actual surface of the sun.
And we've already talked about these sunspots and how the surface, like the sun, is more active. Would that affect it?
Yes. So all of these features we see around the sun, from things like sunspots and prominences, they're all really driven by the sun's plasma, these charged particles that make up the sun, and these magnetic fields. And yes, we've zoomed in here on some of these features on the surface of the sun, and we can see those two sunspots on the left there. These are the same sunspots that we can see in the smaller images on the right of the screen there. So yes, sunspots also caused by the sun's magnetic fields. These are areas that slightly cooler than the surrounding areas. So when we look at them on the screen here, they appear a little bit darker because the temperature is slightly cooler.
I like Matt's explanation about the surface kind of tearing apart and it cooling down in there. So they look like just dust or dirt on the lens. And are they? How big are they? They look, I don't know, it's difficult to assess.
That's the thing. It's easy to lose perspective because when we see them here, these sunspots really do look like just tiny dots. But what we have to remember is that the sun is absolutely enormous. So these sunspots that we're looking at, they are also much bigger than we realize. In fact, what we can do, Anna, is we can bring up a little size comparison to really show just how big these sunspots are. What we're going to do is we're going to briefly bring up a graphic showing the sun, and just as a comparison, next to the sun, we have got an image of the Earth to scale, showing the size of the sun and the size of the Earth to scale. And we can compare the size of these sunspots to the size of the Earth next to the sun. And that should give us an idea of just how big these sunspots are. So let's bring up the size comparison. And there it is. There is the size of the sun's disk, and that is the size of the Earth to the same scale. So now if we go back to these sunspots, we can see that they are as big or bigger than the Earth. In other words, they are enormous.
And also we can see here on this zoomed in image of the sun that it's lighter in the middle and darker towards the edges. What does that mean?
Right, this is an interesting effect here. This is the limb darkening effect, where essentially when we look to the center of the sun, we're looking down deeper into the middle of the sun, whereas when we're looking to the edge of the sun, we're not looking so deeply into the sun. This means that the center of the sun appears brighter, and around the edge of the sun there, it's appearing darker, a phenomenon known as limb darkening.
There's a whole science to this. So remember to check out timeanddate.live. We're going to be back soon. On timeanddate.live, you can find our news feed with live updates. We've got background info about the eclipse. We've got behind the scene images of people setting up their eclipse. It's also a bit of a special eclipse. It's actually a hybrid eclipse. So we're going to be talking a little bit about why this eclipse is called a hybrid eclipse, and we'll talk more about that when we are back. See you soon. And welcome back. You're watching a total solar eclipse here on timeanddate.com, and we're watching some gorgeous images there from our mobile observatory, Time and Date and Perth Observatory in Exmouth, Western Australia. We've got a couple of other smaller feeds there on the side. We've got MIT feed there on the top, and another one from our mobile observatory. There's a lot of Exmouths going on today on our screen. We're closing in on totality. You can follow the progress on our timeline there. So we're about, looking at UTC time, about 50 minutes away from totality there. And we have to mention that we're very grateful for all the news groups, media outlets, and other groups that are redistributing our content today. We've had a lot of emails and Zoom calls and conversations before the event of everyone that want to see this eclipse, because pretty much only seen from this little peninsula in Australia. So we're lucky to have images from there. We also want to include a thank you to our friends at Astronomers Without Borders. It is Global Astronomy Month in April, and we're part of it with this live stream here. So, we're really getting into the deep part of the partial stage at the moment, and it's looking gorgeous. So, we've got the moon's shadow here. Where is it? And how big is it? Because it's looking fairly spectacular at the moment, Graham.
Yeah, as you say, we're really getting into it now. Those sunspots that we were looking at earlier, Anna, have gone. They've been eaten away by the moon. We will see them again later, of course, during the second partial phase after totality, when the moon uncovers the sun again. So yes, the moon is moving across the face of the sun. The shadow of the moon is being cast down onto the earth. And today, the moon's shadow is covering Australia. It's covering Southeast Asia, and a lot of places are getting a partial solar eclipse today.
That looks like this.
Which looks like this. Exactly right. Now, of course, what we're really interested in today is totality. The moment when the sun is completely covered by the moon. Now, if you see totality, you are in a very special part of the moon's shadow, because the darkest part of the moon's shadow in the very center is called the umbra. If you're standing in the umbral shadow, that is where you see the sun completely blocked out by the moon. Now, this darkest part of the moon's shadow, the umbra, this has touched down on the Earth. There is a total eclipse going on right now in the Indian Ocean. And the umbral shadow is moving across the globe at thousands of kilometers an hour or miles per hour, heading towards the Northwest Cape in Australia. It will be arriving there in about, 35 minutes from now. So the question, as you say, Anna, is where is the shadow now? Where exactly is the moon's umbral shadow right now? Well, we can go and take a look. We do have a live shadow map, which will show us exactly which part of the globe is experiencing a total solar eclipse at the moment. We're going to show you this map. It will show the Indian Ocean. It will show the coast of Australia. There will be shading across the map to show the areas of the globe that are getting a partial eclipse. In the middle of the map, we will see a very narrow strip, the path of totality, the very narrow corridor where the moon will appear to cover the sun completely. And somewhere over the Indian Ocean, we will highlight where totality is happening now. It will be just a very, very tiny dot on the map, because today's the moon's umbral shadow is very small. It's around about 40 kilometers, just about 25 miles across. So it's a very small shadow, as we say, over the Indian Ocean. Well, okay, let's bring up the live map and let's have a look. So there we have the Indian Ocean, and there, about halfway up the screen there, that small red dot, that tiny red dot, that is where totality is happening at the moment. That is the moon's umbra, and it is rushing towards the coast of Australia at thousands of miles per hour.
And there's something really special about this eclipse while I was rushing towards, and I was mentioning it earlier. It's a hybrid eclipse. What is that?
That's right. So the interesting thing about today's eclipse is that when we have these eclipses of the sun, sometimes the moon is slightly closer to Earth and is slightly bigger in the sky. Then it can really cover the sun completely, and that gives us a total solar eclipse. At other times, the moon is slightly further away from Earth, and it appears slightly smaller in the sky. For these eclipses, the moon isn't big enough to cover the sun completely, and it gives us an annular eclipse, also called a ring of fire eclipse, because the moon gets silhouetted against the sun, and you see just a narrow ring going around the moon. Now, for today's eclipse, the moon is just at almost the halfway point. Today, the moon and the sun are almost exactly the same size in the sky. That's why the moon's umbral shadow is so small today. That's why we only have about 1 minute of totality today. It's a very short totality. And we saw that path of totality going across the map from the Indian Ocean, across Australia, across Indonesia, into the North Pacific Ocean. The curious thing about today's eclipse is at the beginning and the end of that path of totality, the curvature of the Earth means that somebody standing at the start or the finish of that path is actually a little bit further away from the sun because of the curvature of the Earth. This means the distance to the sun is slightly greater. The sun appears a little bit smaller. So very briefly, at the beginning and at the end of the path of totality for today's eclipse, it's not in fact a total eclipse, but very briefly, it is an annular eclipse where the sun actually formed a very narrow ring around the moon. These eclipses, as you say, Anna, called known as a hybrid eclipse, where in one location on the globe you can see an annular eclipse, and in other locations, such as where our telescopes are in Exmouth in Western Australia, it appears as a total solar eclipse.
And you say standing because that's when you're looking up at the eclipse, but nobody will be standing in the Indian or the Pacific Ocean, will they? There will be maybe some lucky marine animals that will see the annular eclipse.
Well, that's right. Yeah, the start and the finish of the path of totality today is far from land, out over the ocean. So no observers actually get to see an annular eclipse today.
Unfortunately. So there you have it. It's a hybrid eclipse, and that's the explanation. So for more details on hybrid eclipses, go to timeanddate.live. We've got explanations about that. We've got other pictures behind the scenes, all kinds of fun stuff that you can find on Time and Date. So have a look there, and we will be back soon to talk about what to look for at totality. It's all happening. It's all happening. I'm excited. So we'll see you back here soon. Welcome back. You're watching a total solar eclipse on timeanddate.com. And we're looking at a really cool image here from our mobile observatory in Exmouth, Western Australia. It's the Time and Date and Perth Observatory collaboration going on there. And it's a hydrogen alpha telescope, and that means that it's good for picking up these temperature, these differences that we were talking about earlier, including a prominence there on the left side. So it's fun to look at, doesn't it, Graham?
Yeah, it is. As you say, this is a hydrogen alpha telescope, which is looking at the sun at a particular wavelength. It's in the sort of the red crimson part of the spectrum, which is why it's looking as this very this sort of very reddish color, and this is a wavelength at which the hydrogen atom is very strong. And since the sun is mostly made of hydrogen, this gives us a very, as you say, it's a very interesting look at some of the activity that is going on around the sun. As you say, that lovely prominence there on the left edge of the crescent sun.
So we've got other views as well, and they have different filters, different kinds of telescopes, and that's why they look so different from this hydrogen alpha telescope view. We're about 19 minutes, I think, or less away from totality, and we want to talk a little bit about what we can see in the sky during totality, because during totality, we're going to leave the screen. We're going to leave everybody to enjoy the view on their own without us blabbing here in the corner. So what can we expect from totality?
Yes. So as we move towards totality over the next 15 minutes, that crescent sun will get thinner and thinner. It really is looking like the crescent moon there at the moment. That is still, of course, the sun. This crescent gets thinner and thinner. On the ground in Exmouth, things will start to become darker as more and more of the sun is eaten away, until in the final moments before totality, around the edge of the sun, we start to get our very first view of the solar corona. This is the sun's outer atmosphere. It extends out into space around the sun, and we may start to see its sort of ghostly appearance just before totality begins. The crescent sun gets thinner and thinner. The two horns of the sun get closer and closer until we come to an effect known as the diamond ring. This is where the opposite ends of the opposite horns of the sun meet in a final
a flare.
Burst. Yeah, right. A final jewel of sunlight. And coupled with the solar corona, which is now starting to appear around the edge of the moon, it really gives the impression of a jewel set in a ring. So it's commonly known as the diamond ring effect. This final bright flare of sunlight, it then starts to break up into small blobs of light known as Bailey's beads, named after the 19th century astronomer Francis Bailey, who was one of the first astronomers to describe this phenomenon. This is where we're looking at the final rays of direct sunlight coming to us through valleys on the edge of the moon's surface. Bailey's beads disappear one by one. And when the last Bailey's beads has disappeared, that is then the beginning of totality. At this time, we might also catch a glimpse of the chromosphere. This is a reddish band around the visible surface of the sun. Again, a lot of these things, they're there all the time, but we only get to see them when the moon is blocking out that bright, visible part of the sun's surface. So we may just see this reddish chromosphere, and then we are into about 1 minute of totality when we're hoping to enjoy a view of the solar corona.
And during that totality minute, Matt and Stefan are going to be super busy. They're going to be taking off filters, off their telescopes, and making sure that they're going to catch that really faint solar corona.
That's right. And this is the big challenge with solar eclipses, is that they start with the sun's full disk, the dazzlingly bright sun. And at totality, we're going right through to the solar corona, which is just much, much, much fainter. It's about the same brightness as a full moon, which interestingly does mean that it doesn't get completely dark on the ground during a total solar eclipse. It gets about as dark as it does on a full moon night. But it is a completely different level of brightness to that of the sun itself. So yes, the challenge is taking off filters, making adjustments, and switching telescopes from the view of the bright sun to the solar corona.
And if you're on the ground there and you're enjoying the solar eclipse, you might notice that the birds are going to go a bit crazy in the sky. They're going to think that it's nighttime. The temperature might be a bit cooler. It all feels very surreal. I remember from my one experience of seeing a solar eclipse, total solar eclipse. I'm going to see many more. So for those on the ground, this is a special moment, but they have to keep those eclipse glasses on.
Right. We talked earlier about the importance of not looking directly at the sun without proper eye protection. Proper eye protection means certified eclipse glasses from a reliable source. This still applies right through the partial stage of the eclipse. It applies right through the diamond ring effect and Bailey's beads. This is still part of the partial stage of the eclipse. It is only when the final one of Bailey's beads has disappeared, that's when totality starts. That's
when you can take them off.
That's when it's safe to take off the eclipse glasses and enjoy the view of the solar corona, but only very briefly, because totality lasting for, at our location just south of Exmouth, it's 1 minute, 3 seconds. In Exmouth itself, it's a little under 1 minute. It's about 58 seconds. Eclipse glasses have to go back on before the end of totality, before we get the same effects happening after totality. We see Bailey's beads, we see the diamond ring, we see the crescent sun re-emerging. Eclipse glasses have to go back on before those effects start. So it is only a handful of seconds that we can remove eclipse glasses and enjoy the view of the solar corona.
So stay put if you're not on the ground out and having this fabulous experience, and stay put here. We're going to leave you so you can enjoy the whole build up to totality and totality itself. And we're going to try to show it from several different angles. So we're excited about that, and stay put because we'll be back after totality is finished and we've got a lot more of show to go through.
Sunday.